to talk to you about an introduction to WebAssembly or Wasm from the browser to the SpiderLightning cloud. I'm Danilo or Dan, and I'm sure from the title itself we have tons of questions, right? Like what is Wasm? What is WebAssembly? What is SpiderLightning, right? But we'll try to answer all those questions little by little. But we'll start with an easy one, which is who is this guy? So I work as an open source software engineer, well, here at Microsoft in Azure's containers Wasm upstream team, and work primarily with Rust, WebAssembly. On my free time, I like Rust and Wasm so much that I also like to teach others. I have a YouTube channel called Dan Logs if you want to check that out. But when I'm not working with Rust and Wasm, you can usually find me watching Star Trek, playing Super Smash Bros. Ultimate, or going on 10K interval runs here at David Lamb Park. So yeah, that's me. I have my socials there. If you are into Twitter or GitHub, whatever, you just can follow me there. And so let's get started. The agenda for today is we'll go on a bit of a time travel. We'll start it back in 2018. I'll give you a 2018 introduction to WebAssembly. We'll move forward to the exact same thing in 2019, then 2021, and we'll finish off with a 2022 getting started Wasm guide with SpiderLightning and Slight, which is what I actually work on here at Microsoft, SpiderLightning and Slight, the two projects. So my goal back in 2018 will be to introduce you to what WebAssembly itself is. So hopefully you'll leave 2018 with that knowledge. Then we'll move on to 2019. I'll introduce you to something called the Wasm system interface. Then 2021, we'll move forward to the Wasm component model. And again, finish off with the little tutorial at the end. And as you can probably tell, we have 4+ demonstrations. Because, I mean, what could go wrong with 4 live demos, right? So let's go. We'll hit rewind a little bit on our remotes, and we'll go, like I said, to 2018, where I'll give you a 2018 introduction to Wasm. And we'll understand why we're time traveling in a bit. So what is Wasm? When people ask me that, I like to tell them that Wasm is a language-agnostic binary format and a compilation target. And people usually follow that statement with a couple of very reasonable questions, like, what do you mean by language agnostic? What is a binary format? And what is a compilation target? Those are very reasonable questions. So to explain, I'm not sure how many people in the call or here are developers, but going from first principles, your computer sort of understands, right, in a crude simplification, ones and zeros. So when you get your program, like my awesome program whatever, sort of stressing the whatever there for being language agnostic, meaning that it doesn't really matter the language, you pass it through this magical cylinder that is the compiler. You compile it, you get ones and zeros, right? So that's sort of how the usual flow of things go. With WebAssembly, it's pretty similar. You get my awesome program whatever, you pass it through the magical compiler cylinder, and you get at the end my awesome program wasm. So you get this wasm module, and that's the binary format that you get. So again, language agnostic. That's because we have my awesome program whatever. Doesn't matter the language that you're in. If you're with Rust, you're with Go, you're with C#, F#, Zig, Grain, assembly script, whatever, you can compile it to Wasm. And you're compiling to Wasm. Wasm is a compiler target, and it is a binary format like the ones and zeros that we just saw in the previous slide. So that's the idea there. And then that usually gets followed up with, cool, why do we need this, right? Like, why are we not happy with our old binary format that's been powering applications since forever? And why do we need a new binary format? And before I answer that, I want to turn our attentions to the browser, which is what WebAssembly came out for in the beginning. So again, it's 2018, and there are tons of JavaScript web frameworks on the rise. We have like React.js, Next.js, Vue.js, whatever. I'm not a front-end developer, so you can fact-check me if those actually came out in 2018. But my point is, JavaScript is sort of everywhere. And with that, we're starting to push it to go way beyond what it was originally designed to do. So like heavy computation for games and yada, yada, yada. And my point is, we're asking JavaScript to be very, very fast. So another reasonable question is, so is JavaScript fast, right? Like, can it do heavy computation for games? And the answer is kind of yes and no. That really depends on the engine that a JavaScript runs in and optimizations to the engine and how it goes. So a better question really is, how slow is JavaScript? And to demonstrate, I prepared a little example, which we're not going to run live because, as you can tell on the bottom, it took 31 minutes and 40 minutes. So we won't do that here. But this is a little program on the, depending on how you're looking, on that side, the 31 minutes one, that is a C++ program that is compiled to WebAssembly. And to find all prime numbers from 3 to 1 billion, it took 31 minutes. And with JavaScript, it took 40 minutes. So when people ask me, why do we need Wasm? This is a good example. We need it to save those 9 minutes of computation time. We need it because the performance on the web is getting more and more critical. So we need it because it's fast. WebAssembly, it's near native computation time. So the compiled code that you have on your native computer, on C, C++, whatever, you get almost just as fast on the browser with WebAssembly. Cool. So we get that 20%, 25%-ish improvement in time. But that's not all. Because for the first time ever, JavaScript's virtual machine, which is where JavaScript runs, has opened up to allow WebAssembly to run in it. And that's a big differentiating factor for other web technologies like Java applets, if you were around for all those little games that came out with Java. That's the big difference. All those technologies that took a stab at the web, they were not running in the JavaScript virtual machine. They had to sort of figure out their own sandboxing and all that story. And that's great because now Wasm is benefiting from years and years and years of security improvements that JavaScript virtual machine got. So we need it not just because it's fast, but also because it's safe. But I'm not done. People really like writing code only once. That's why so many technologies like React and React Native come out, right? In this example, you can easily sort of interchange code between, say, I don't know, the web and your mobile. WebAssembly allows you to do that as well. So you can write, okay, your legacy 1980 C code, and you can now modernize it and put it on the web with WebAssembly. So we need it, not just because it's fast, not just because it's safe, but also because it's portable. So to recap, Wasm is a language-agnostic binary format and a compilation target that provides speed, safety, and portability. Yay! We made it. So now it's demo time, and that's our very first demonstration to end the 2018 year. So my point with this demo is to sort of demonstrate how easy it is to sort of just get whatever C code and get it on the web and get it running. And to demonstrate that, I'm going to open the terminal, and I'm going to start a new project. Let's make that way bigger. Kind of, mostly. Hopefully everybody can see that. So in here, what I'll do is I'm going to use this project called Tarantella. It's a package manager that I wrote myself, and I'm using that just because it makes it very easy to start a new project, build it, and run it. So to use Tarantella, you do tapm, that's Tarantella package manager, new, and you create a new project. I'll call it Vantalks Demo 1. Okay, we created a new Wasm app at Vantalks Demo 1, and I'll CD into it. So I'm in it now, and let's take a look at what's inside. So that's quite a bit, but you can see we have a makefile. If you're not familiar with makefiles, it's just something that will make it easy for us to compile our code with a couple of rules that just make you not have to repeat codes over and over. You have a build folder, which is empty right now, but after we build our code, we'll presumably have something in there. Then we have an index file, index.html. That's what will be rendered on the web. We have a source folder. Let's take a look inside of that. Inside a source folder, we have a main.c file. And let's take a look at that. Source main.c. That's a very simple file. You can see we're bringing in two things. We're bringing in IO, that's for the printf function, so to print the hello. And we're also bringing something in called inscription. Inscription is the WebAssembly compiler. So it's the WebAssembly compiler toolchain that will actually, it's the cylinder in the previous example, right? So it's what we're going to get our C code and give us the Wasm module. And then we have a tag saying Inscription keep alive. That's what's telling Inscription that we want to have this print hello function available and exported to the browser. And then that's just calling the usual libc printf hello. And then our main function just calls print hello. Cool. Let's continue. So we're at source. We saw the main.c file. We have a tarantella.toml file. This file is sort of like a package manifest or a project manifest. It just has things like the name of the project and the version, yada, yada, yada. And then to finish off, we have dependencies and releases. Those are just two folders that we're not really using. We won't get complex into getting dependencies or making any releases onto GitHub because, I mean, we don't need to. So that's sort of about it. It's a lot, but it just makes it easier so that you don't have to create those things yourself. Cool. At this point, I think we're ready to build it. And to build it is just as simple as saying tap and build. And if nothing fails, there we go. So we see we made a call to AEMCC, so that's the Inscription compiler. We're creating a main module of Wasm, and we're outputting that ventox demo1.js. JavaScript? I mean, what do you mean? Shouldn't it be a Wasm module? So let's take a look at that build folder. And you see that we have two things. We have JavaScript, so JavaScript is still there, and we have Wasm. So what that JavaScript file is doing is just a bit of glue code to get that Wasm working in the first place. And you'll see why we need that in a second. But to demonstrate that, let's actually do a run. So we're doing tap and run. And now we have an address that we can follow to see it on the browser. So let's do just that. And there we go. We get hello Tarantella, which is not really what we were expecting, right? I thought we were going to get a hello. But the hello is there. It is just on the console. And now this brings me back to that JS file. So if we go in here and we cancel out of this JS file that we had back in the build file, folder, this JS glue code is what's actually telling Inscription to tie in our printf calls to console logs. And we could take a look at that just for fun. Let me open this on code. Sure, I'll trust the authors. Go to JS, and you see we have tons of code, but we can find a module print, and so you can see that all print functions that are not print error are binded to the console log function. So this is what Inscription is doing with that JS. All right. That was our first demo in the books. No failure so far. Let's go. So now we can hit fast forward a little bit. We're now in 2019, and I'm going to give you an introduction to Wasm in 2019. So 2019 is special, and I separated this talk in little sort of like time travel pieces because in 2019, this announcement came out. This announcement was from Mozilla, and they said, today we announced the start of a new standardization effort, WASI, the WebAssembly System Interface. And the title said, Standardizing WASI, a system interface to run WebAssembly outside of the web. So now WebAssembly was so successful that people wanted to take it outside of what it was designed to do, to be in the web. Now I wanted to run it sort of everywhere. But so what is this Wasm system interface, right? And I want to bring back the fact that Wasm, to explain, the Wasm is portable. And to quote the design spec, portable means that it makes no architectural assumptions that are not broadly supported across modern hardware. So what that means is that Wasm, if we don't tell it sort of how to talk to the system like Inscription did with the console log bind, it doesn't really know what to do. It doesn't know what to do with that printf call. It doesn't know what to do with anything. So what WASI is doing is it will tell any operating system what to do when you get sort of like a printf call. So in this example, it could like route or libc calls to display in an X operating system. And what better way to explain that than another demo? And this time, we're going to move away from C, and we're going to create a Rust project. We don't really have to know Rust. It'll be pretty simple. And all I'll do is I won't make anything WebAssembly special. I'll start just a new Rust project, and I'll call it Vantox Demo 2. Very creative name. And there we go. So if you don't know Rust, Cargo is just Rust Package Manager. This is just a normal Rust project, no special WASI things. So let's go inside it. Oops, Van2. We listed, and we have two things. We have a cargo toml, and we have the source, cargo toml, package manifest, and the source. As you'll see, it's a very simple hello world. So now our objective here is to not display it on the browser. We want to have it on the terminal. We want to have that hello world display right there. And to do that is, again, very simple. All that we do is we say cargo WASI build. And in less than a second, we have a build done. So if I now ls it, you'll see that we have a new target folder. And inside of it, Wasm debug, we have Vantox demo 2.wasm. And this time, no JS, nothing, no web, just that Wasm module, which we can run by doing a cargo WASI run. Hello world. So it's pretty anticlimactic, right? We just got a hello world, and it's like, wow, amazing. So for us to appreciate that a little more, I want to actually display WebAssembly. So let's go to code and actually take a look at that binary format. I'll trust the authors. So let's go to target, Wasm32 WASI, debug, and let's take a look at our Wasm module. Oh no, this file is not displayed in the editor because it's either binary or uses an unsupporting text encoding. So that's a problem. We can't view it directly, but as I told you, this is binary. So you can sort of assume that we can take a step back and view it in sort of an assembly-like format. And if you assume that, that will be right. We can. And to do that, we can use a toolkit called WABIT, which stands for WebAssembly Binary Toolkit. It provides us a command that's called wasm to what. And what here stands for WebAssembly text format. So it'll give us sort of an assembly-like language to view it. So we can do a wasm to what, and we can pass in our target, wasm32 WASI, debug, Vantox demo2 dot wasm. And by default, this command is just displayed on the browser. That's sort of a lot to see. So I'm just going to pipe it into a file, which I'm going to call Vantox demo2 dot what. All right, as I told you, it's quite a bit. So let's take a look at that inside of code. And there it is. That is our assembly-like language displaying everything that WebAssembly is doing to get that hello world printed. So hopefully this gives us more of an appreciation of everything that's happening, because it is 27,685 lines of code. Amazing. So that's everything that WebAssembly is doing to get that little hello world going. And that is another demo in the books. So again, we're going to hit fast forward, and we're going to move to 2021. So we skipped a year. And why did I? Did WebAssembly just die, right? Did people stop working on it, and I don't have anything else to say? And the answer is no, it didn't. In fact, the whole ecosystem has just been maturing to keep up with everything that people want to do with Wasm. And to show you an example, I have an article that hopefully you can read there on the side. It says that Google Earth comes to browsers thanks to WebAssembly. And that's an article by Jesse Beck and Jordan Mears, a software engineer and a tech lead manager for Google Earth. So in fact, it hasn't died, and it's grown a lot. And it offers now capabilities to go even beyond POSIX, so like that OS API, right? We can go beyond that. But more about that in a second. Because now I actually want to introduce us to something else. I want to introduce to the WebAssembly component model, which we'll actually explain that POSIX, but just in a bit. Because, so attentive observers might have noticed that in that WAT file, we only had 4 types. We had an i32, we had an i64, we had f32, and we have f64. So we have integers of 32 bits, 64 bits, and floats of 32 bits and 64 bits. That is it. So that makes it pretty hard to make any non-trivial application that does anything like, I don't know, interoperating between runtimes or language boundaries. That will require significant effort, like pointer arithmetic in memory to like have a string or anything like that. So aside from allowing us to go beyond POSIX, which is something that I'm just hinting for the future here of the talk, the component model allows us to address this limitation of only having very basic types. And it does that with WIT, or WebAssembly interface types, which is an interface definition language. So yet another language that allows us to write something sort of like this. So you can define like a resource, KV being a key value store. And this is just an example. And then you can define very high-level functions like static open, which you can pass a name to open a key value store, or a get function where you can pass in a key to get a value in your key value store, set a key value, and keys to get a list of keys or delete and so forth, like any key value store. And yeah, so now we have the possibility to do this with the component model. And it's demo time. So now I've actually prepared this demo ahead of time. It should be in my repos and inside of VT, yeah, VT demo 3. Cool, so let's open code in here. And now, so we have, okay, it's still there, good. So we have this file, right? And that's just sort of like a blueprint for something that you could implement. So how do you use that? And that's where that is not what I want to do. That is not what I want to do either. I want to open the terminal. Okay, there we go. You can tell I use VS Code a lot. And so what I want to show here is that we can, and WebAssembly allows you to create bindings for this interface in specific languages. So, and to do that, you can do something, you can use a technology called WIT bindgen or WIT binding generations. That might not make a lot of sense now, but to explain, again, demo. So we'll do a WIT bindgen. And again, we have several languages. I'll show C just because why not? I'll do another one later. And I'll do a C export. Export here means that we want to create the bindings for someone that will implement that interface. So that's an export. If you were making use of the interface, that will be an import. And you pass in your WIT file, so vtkv. And we have WIT bindgen now found. That's because it's called bindgen. And there we go. Now we have 2 files. We have a header file for C. So that's actually very similar to our interface. We have, I don't know, a bunch of utility functions that will do sort of things like the point arithmetic for us, which will be displayed in the KV C file. So again, I don't want to go into specifics here, but my point here is that you can now have high-level types of WebAssembly described in WIT, and you can use WIT bindgen to create bindings for an X language, just like that. And I really want to stress what I said here, an X language. It's so wild that you can create even bindings for something like Markdown, so like a markup language. So let's do that. We'll do WIT bindgen, Markdown, we'll do export, whatever that means, and kv.wit. So you see it created bindings.html and bindings.md. So let's see what that is. We open, and let me actually render that if I can. And there it is. We created bindings for a WebAssembly interface that is just a Markdown file. And obviously, this is just for fun, but it's just displaying that you can create bindings for sort of anything that you want to. And you can have high-level types in WebAssembly there, even in something like Markdown. Cool. So that is demo 3 in the books. Now we're ready to hit play. We're now in 2022, and we're getting started with Wasm. with SpiderLightning and Slight, which again is what I actually work here at Microsoft, the SpiderLightning and the Slight project. So remember what I said about POSIX and going beyond POSIX, right? These OS APIs with the WebAssembly component model. That's what we're doing with SpiderLightning. So SpiderLightning is a group of WIT files that provides interfaces for sort of common developer capabilities. So something like the key value store that we just saw. That was actually very similar to their very own key value store that we have in the SpiderLightning project. But also HTTP, distributed locking, message queues, PubSub. I mean, you name it, we're probably making it. And I'm saying that we're going beyond POSIX because the SpiderLightning project is actually becoming part of the WebAssembly system interface standard. I'm not sure if you can tell, but that link right there for GitHub, that's github.com/webassembly/WASI proposals. That's a proposal, and that is my name right there. We're proposing for the standard, the blob store, distributed lock service, gRPC, HTTP, key value store, message queue, PubSub, runtime config, and SQL. So these things are going on top of WASI. So now you can imagine we have, WebAssembly, you have a binary format. We have WASI allows you to talk to the OS. And then on top of that, we now have developer capabilities. So you can interact with things that are very high level, like key value stores and yada, yada, yada. And I feel like at this point, a very reasonable question is, okay, we have interfaces, we have all those cool high level types. But again, someone has to implement those things, right? If you use with BindGen and you create the export bindings, someone has to go in there and implement that key value store. And that's where the other thing I mentioned, Slight, comes in. Slight is the other project that we're working on, and that's a host runtime that provides implementations for WIT files for common service or cloud providers, just like Azure or AWS or GCP. So I have here a list from our README showing a couple of examples of implementations that we have. So the distributed lock service, we have implementations for etcd. For key value store, we have implementations for the local file system, Azure Blob Storage, AWS DynamoDB. Then message queues, we have local file system, Azure Service Bus. PubSub, we have Confluent Apache Kafka. And then runtime configs, we have environment variables, user secrets. We also have Azure App Configuration. And HTTP, it's all in there. Those things are implemented. And using Slight, you can make use of it. So you probably guessed it, it's demo time again. So let's actually use Slight. Go in here, and we're going to create another project. We're going to use Slight. So that's, again, the host runtime. We'll do a Slight new, and we're going to create a new Slight project. I'll call this Ventox Demo 4. And I actually forgot something. You have to pass in n. So that's Slight new n Ventox Demo 4. And you have to then specify a version for the interfaces that you want to use. So the interfaces are versioned like that. So I'm going to specify that we want to use the 01 version at opatch. Cool. And the last thing, again, WebAssembly, language agnostic. So we have to specify the language that we want to use. We want to use Rust. We want to use C. Those are the two things that Slight supports right now. I'll choose Rust because I like Rust. And it takes a bit, but hopefully we should have that ready in Ventox Demo 4. Cool. So let's usually our customary ls here. You see we have just 4 things. We have our cargo toml. That's, again, the package manifest that comes with Rust. We have a Slight file toml. That's now the package manifest for our Slight project. We have then a source folder and a WIT folder. Let's take a look first at the WIT folder. So let's go inside of WIT. Let's do an ls here. You see we have a KV, so the key value store that we just looked at an 01 version. And let's go inside of that. So WIT, KV. And you see we have 3 WIT files. So the kv.wit, resources.wit, and types.wit. Let's just do a cat on that KV. And you'll see that it is actually very similar to the one we had, with the only exception that we're not returning strings when we have errors. We're returning an actual error type that is defined in types, but then the rest is sort of all the same. With the one also difference that we don't just support strings for values, we support an X payload that you can handle however you want. Cool, so we have that interface. Now we can, oops, I did not mean to CD. Let's go back in there. So that's our WIT folder. We also have a source folder, but let's first take a look at the slide file. So that is saying that we're using a spec version of 01. That's because our interfaces are version 01 as well. We're specifying a secret store, whatever secrets we have. We want to by default local environment variables. And we're using one capability that is the KV file system. So we're going to use a file system implementation of a key value store. Cool, cool, cool. If we want, we can also take a look at the cargo toml. It's nothing special. It just brings in a couple of dependencies that are useful for handling errors and with bindgen and things like that, and also specifies the name of the project and the version. Cool. Let's now look at the source folder. So we go inside source, main.rs. Again, we have a very simple project. All that we're doing is we're making a call to with bindgen, Rust, and we're passing in the KV wit. So what that will do is we'll create all the bindings in that folder itself, in the file itself. You can ignore the next line. That's just implementing an error trait for our error type. But then what I want to focus on is the main function. In the main function there, what we're doing is we're opening a folder that contains supposedly our key value store that will be created. And we're also doing a kv.set. We're setting a value for hello SpiderLightning, or a key hello SpiderLightning that has a value hello SpiderLightning. And then we're just getting that and printing it. So if everything succeeds, by the end, we'll get hello SpiderLightning in the console. So let's try to do just that. To build it, it's the exact same command that I showed before. You do a cargo WASI build, and that should take something like 6 seconds. So 1, 2, 3, 8 seconds. OK, cool. So that is done. And if I ls again, we have that target. So just to sanity check ourselves, we'll check target. And you see we have a Vantox demo4.wasm, which is what we were expecting. Cool. And now we can run that. We can run that by calling slight. We'll pass in a configuration file. That's our slidefile.toml. And do a run call. And we'll pass in a Wasm module that is inside of target. Wasm32, WASI, Vantox.wasm. Hello, SpiderLightning. Yay. So that's very similar to what we did before, right, with just WASI. But the whole point is that we're actually making use of a key value store, and we're making use of sort of high-level developer capabilities that you might want to use. So yeah, that's making use of the file system one. We can try to change it to make use of something like Azure. So let's do just that. We'll go inside of the slide file. Let's use, we'll use nano slidefile.toml. Ooh, I don't know. I don't want a sudo. OK, nano. And what I want to do here is I want to change the secret store to look at my Azure app configuration. That is not how you spell app. And I want to use, instead of a file system implementation, I want to use an AZ blob. So we're now not using the file system. We're actually talking to the cloud. Now let's exit this. We'll hit yes. We'll save. Cool. And one last change that we have to do is we have to actually change our source code inside of source and main, because we're not opening a folder anymore. We're actually opening my container in Azure. So instead of my folder, we'll say my container, which I've created ahead of time. Hit yes. Now, fingers crossed. Oh, we actually have to build it first. That would not have worked. So let's cargo WASI build, right? So we modified source code, rebuilding, doesn't take much time. And now we'll run that slide. Fingers crossed. There we go. Hello, SpiderLightning. So nothing changed, and that's great. But we know from the slide file that that's actually accessing Azure. And I can prove it by going in here. And I want to nano inside of our main. There we go. Let's change this KV to be not the name of a container that I've created ahead of time, and instead just something random. And I mean, if everything works, this should fail. So let's run again. And there we go. We see that we have an Azure core policies retry policies failed. So we get a 404, right? This doesn't exist. So it is talking to Azure and things are communicating. And this is all done with WebAssembly. And that is our demo for in the books. But that is not all. That is not cool enough. I have one last demo. And this last demo is to sort of just display sort of how far you can go with Slight right now. And to do that, I want to go inside of a folder that's called Slight Kitchen Sink. And in here, we created a chat app. So you can sort of talk with folks. I mean, everybody knows here what a chat app is. And in here, I have to call in a couple of commands. I have to do a make serve and open a bunch of terminals, actually. So let me do that first. And I won't go into specifics of what these commands are, but what you can imagine is that this is serving the front end, and it will also create a Redis server, which is the key value store that we're accessing to store the messages. So I'll do that first, and maybe I can make that bigger. That is not what I want to do. All right, we'll keep it small. Clear. All I'm doing here is I'll do a Redis server that's running. And in here, I'll go into repos, Slight Kitchen Sink, and I'll run make run. So what that did right there, we don't have to look at the details, but that created the backend. And in here, we'll create the front end. And there we go. We have a server listening in that port. Let's grab that real quick and go in here. OK. Let's open another one, because what is a chat app if you're by yourself? And let's put them side by side. So now I can say hello. And there we go. We get hello in the two screens. And now I can also say hi from the other guy. There we go. We get the two highs. So again, we've gone a long way. We started by describing what WebAssembly was, this binary format. We moved on to WASI, this sort of POSIX layer on top of Wasm that allows to talk to the OS. We then move forward to the component model that allows you to define high-level types and go beyond POSIX by defining your own interfaces. And then we move forward to Slight, which defines a bunch of interfaces for things developers use, like key value stores, message queues, pub/sub. And that's the SpiderLightning project. And then you have Slight, which is the runtime that actually creates these implementations for key value stores and things that you would use. And that allows you to make this very cool chat app. And that is it. Thank you for listening. So right there, I have links for projects that I've talked about, like SpiderLightning, on WASI, kind of, Continuity Wasm, Shims. Those are things that I work on my day-to-day. And then just my socials, if you care about that.